Alright, I have a couple of examples for you. Let's work these out. So in the first one, a basketball player throws a basketball straight up. The basketball is thrown directly upward from the ground and returns to its starting point in 0.8 seconds. We have 3 questions to answer. How long did the ball take to reach its maximum height? What was the initial velocity of the ball? How high did the ball go? So our total time in the air is 0.8 seconds. Get that going. So let's draw an illustration. The ball goes up and comes straight down. It's let go and returns back to its starting point in a total time of 0.800 seconds. So I'm going to add t total at the bottom, or as a subscript to the time. It says how long did the ball take to reach its maximum height. So we just need to cut the total time in half. So t1/2 is 0.400 seconds. So just like you were doing on Friday with the air rocket lab. What was the initial velocity of the ball? So we want to know VI when the basketball player let go of the ball. VI is our unknown. We know T to the tip top took 0.4 seconds. You remember what the velocity at the top is? If we call that VF, that's 0 momentarily. So VF is 0 meters per second. And our acceleration, since the ball's going up and down, I want to use negative 9.8 meters per second squared. Think about your basic equations. I'm choosing the acceleration equation, VF minus VI over t. I want to isolate VI, so I'm going to rearrange. I'm going to multiply both sides by t, and then I'm going to add VI to both sides. Let's get to this point, see if you can follow it. We've done it a whole bunch of times. I want VI to be by itself, so now if you subtract AT from both sides, you have a working equation. Let's put in our numbers. VI is going to be equal to VF, which is 0, minus a negative 9.8 meters per second squared. Move this over. Times 0.40 seconds. Your 9.8 becomes positive because we're subtracting it. And use your calculator. I think I've already done this. And I have 3.92 meters per second as my initial velocity. Move these guys over. So there's your answer to part B. Let's look at part C. How high did the ball go? So this time, we want that distance. There's our trajectory. Oh, I think it's going higher this time. This time, we know VI is 3.92 meters per second. We still know A is negative 9.8 meters per second squared. To get to the highest point, it took 0.4 seconds. And we know VF at the tip top is 0 meters per second. I want to find displacement. I'd like to use D equals VIT plus 1/2 AT squared. D will be what we're looking for. VI is 3.92 meters per second times the 0.4 seconds plus 1/2 negative 9.8 meters per second squared multiplied by 0.4 seconds squared. Important that you have that negative on there. I want to verify my answer, so I'm using my calculator. 3.92 times 0.4 plus 0.5 times negative 9.8 times 0.4 squared, and I have a displacement of 0.784 meters. So it doesn't go up very high. And that's your first example. Let's do one more. Here's the full problem. A young girl drops a coin into a wishing well. She sees the splash of the coin in the water at the bottom of the well. Let's see if I can add that space. Oops. There we go. She sees that splash of the coin in the water at the bottom of the well 1.7 seconds after she drops it. We have two questions posed. How far is it from the top of the well to the water, and how fast is the coin traveling when it hits the water in the well? Fix my typos. All right, so we know it takes 1.7 seconds for the little girl's coin to hit the water. So, first question, how far from the top of the well to the water? So, she's dropping the coin. There's a nice little coin. It's splashing in the water in the well. It's going in one direction. That time is 1.70 seconds. Now, it's falling in one direction, so I like my reference point 0 to be at the water level, so I can use a positive gravity because everything's traveling in the same direction. So I'm using 9.80 meters per second squared. We want to know D. Now a little trick, let me go back to the last page. When it says somebody drops something, the initial velocity is 0. So VI is 0. So, thinking about my equations, I'm going to choose that one we just used, VIT plus 1/2 AT squared. My initial velocity is 0, so that's going to go away, and my D will equal 1/2 AT squared. So we're ready to put our numbers in. D is equal to 1/2 oops, let me plug in my 9.8. Have to open that up. There we go. 9.8 meters per second squared. My time interval was 1.70 seconds squared. Okay, on your calculator, you should be punching in 0.5 times 9.8 times 1.7 squared, and we get an answer of 14.161. Let's go to 3 sig figs. So I'm going to that spot. So I have 14.2 meters. That's the distance to the water. Let's see what the next question asks. How fast was the coin traveling when it hit the water in the well? So we still have T. T was 1.70. Acceleration due to gravity was positive 9.8 meters per second squared. We also know the distance to the well is 14.2 meters. We know that VI is 0. We're trying to find its velocity at that split second before it hits the water. Alright, so she's dropped it, and we want to know VF right before impact. Now, I think there's a few different ways. I think I want to go back to the acceleration equation, VF minus VI over t. I'm going to solve for VF. VI is 0, so you can see that AT is equal to VF. I like to write it VF equals AT. There's my working equation. So let's put in our numbers. VF is going to equal 9.80 meters per second squared times 1.7 seconds. I'll bet you get the same answer. Before rounding, we have 16.66. These are meters per second. We need 3 sig figs. I'm going to round to 16.7 meters per second. Really fast. Of course, we're ignoring air resistance, but still, gravity makes it go quite quickly. All right, that's it for examples. See you later.